Lesson 2 in our algebraic vectors unit talks about some operations that you can do with them. And this is really where we start to really expand, what vectors are good for and, what they allow us to do. Now, there's a very common teaching strategy in this unit which I am going to follow, which is to complete tasks in 2 dimensions using algebraic vectors so that you have an easier time visualizing what you're doing in 3 dimensions. Of course, it's difficult for us to visualize 3-dimensional operations, much more accustomed to 2D. So sometimes in this unit you're going to come across things where you think, I already know how to do that, why do I need a new way of doing it? And the logic is, yes, you already have a way of doing it, but your way only works in 2D. It doesn't work in 3D. So the reason you're learning a new strategy in 2D is because if you can master the strategy in 2D where it's not so hard, you have a better chance of sort of making sure you grasp it in 3D, right? So like for instance, the intersection of 2 lines in 2D, you already know how to do that. I mean, you set the equations equal and look for the variables and so on. So you might wonder, like, why are we learning new ways of writing a line, using vectors? And again, the analogy is we learn it in 2D where we're sort of safe, it's easier, we understand it, and then we sort of, upgrade it to 3D, and hopefully it's not such a big jump. So let's start. So again, you're going to see a lot of questions that have a little R2 beside them, again indicating that we are in 2 space or 2 dimensions versus operations in R3 where we are in 3 space. Now it says, given P and Q, find the coordinates of vector PQ. Okay, so remember, what is vector PQ? What does that vector mean? It means if I were at P, how would I get to Q? Right? It doesn't mean I'm at either of those places, right? It's just the instructions for how to get from P to Q. Right? It's like if you tell a friend the directions for how to get from, school to your house, but you're talking to your friend when they're at their house, right? The vector is the directions. None of you are actually in the location that's being described, right? Because you're not a point, you're not a line. A vector is just an abstraction. It's how would one get from this spot to that spot. So anyway, to get a vector is a very easy formula. You just do destination minus origin, and that's it, and you do it for each component. So the destination is 4, 1, and you're subtracting the origin, which is negative 2, 3, and therefore the vector is 4 take away negative 2, comma 4. Sorry, it thought I was writing something else. 4 take away negative 2, comma 1 take away 3, and that vector is 6, negative 2. So then what you would write is PQ, so vec PQ is equal to 6, negative 2. Okay, and this actually also gives us another equation that we can use. And again, you could just count this, right? You can just go from P to Q. It's like 1, 2, 3, 4, 5, 6 over and 2 down, right? That's all that's saying. But it does give us an interesting formula, which is this formula, right? Q equals P plus the vector. So you can say that a point is equal to another point plus a vector, because now what you're saying is there's a specific place you have to start, P, then you have to follow the instructions PQ, and then you will arrive at the point Q. Okay, that you can do. So just to sort of understand why how these things are slightly different from one another. Okay? Again, a point is a location in space. A vector is a set of instructions. It's not a physical object. Okay? I mean, it is a physical object, but it doesn't have a location. Let's put it that way. Okay. Now, when you do vector operations in R3, okay, it's not that bad. U is a vector. It has 3 components: U1, U2, U3. U1 would be its x coordinate, U2 would be its y, and U3 would be the z. Again, V is another vector, right? 1, 2, 3. And P is a point, and P2 is a point. Again, These things look very similar. But a point and a vector are not the same thing. Notice that in a point, they say x1, y1, z1, whereas in a vector, it's u1, u2, u3. So all three letters are the same, reminding you that they are all part of vector u, where here, all three letters are different, reminding you that they are each a different coordinate for the same point. Okay? So let's do some operations in 3 space using 2 points and 2 vectors. So again, let's just, I think an easy way to do this would be to just demonstrate visually. Let's just make up, so let's say vector u, let's make up a random vector u is 1, 2, 3. And then a random vector v will be 2, negative 1, 4. Okay, so there are the two vectors. You can see they're both pointing up because the z's are positive. They're both pointing in a positive x direction, which is towards the red positive. But you can see only one of them is pointed in a positive y direction. One of them is pointed in a negative y direction because it's negative, its y is negative. Now if you add these things together, it comes up with this third vector. Okay? And how did it do that? Well, it added the two x's, 1 plus 2 is 3. It added the two y's, 2 plus negative 1 is 1. And 3 plus 4 is 7. So again, adding vectors in 3D is very, very simple. All you have to do is add each component. And again, subtracting them is the same thing. To subtract them, all you're going to do is subtract each component. So let's say we did u minus v, right? So now it comes up with this other vector that's going down. It's still a parallelogram, by the way. It's just kind of harder to see it, but there is a parallelogram here. Maybe I'll draw it out for you in a second. But how did it do this? I mean, it's simple. It did 1 take away 2, that gives you negative 1. 2 take away negative 1 is 3, and 3 take away 4 is negative 1, and it drew that. Okay. Now again, the parallelogram here, so let's draw the parallelogram. Let's work on some instructions here. So let's start with a point O. The point O is the origin, right? And where would I end up if I followed vector u? So let's go O plus u. Now you see what it does differently here. Because I started with a point and added a vector, it knows I'm talking about a point. I'm talking about that point, and that point is O plus u. Now let's make another point, O plus v, and that's going to be over there. And then let's make another point, O plus v plus u. That's up there. Now if we do a vector that joins b to c and a vector that joins a to c, we're going to get the parallelogram we would have got in Unit 6, right? And if we join a vector from b to a, we get the subtraction that I did before. You see the subtraction I did is in the dotted line down here. That's the exact same thing as the parallelogram that I just drew across the center of the parallelogram. So what you're doing in 2D still works in 3D when you're adding vectors, just a little bit harder to visualize, but it's still very, very, very similar. Anyway, so we can add vectors, we can subtract them. It works the same way as in R2, except you don't really need to do any cosine law or whatever. You can just add the components together. Now, when you're doing scalar multiplication, you just scale up each element. So let's say I wanted to do 2u. Okay, so let's hide some of this stuff because I think this is getting a little cramped. Okay, so let's hide these a and b points. So I'm just going to, here's again u and v again. Now what did I draw here in this second vector? Let's just change the color of this so it's... Okay. The red vector here is just 2u. I took u, I doubled each component, 2, 4, 6 instead of 1, 2, 3, and it's the same, it's pointing in the same direction, it's just twice as long. Okay, and that's all. And how did I do that? You know, again, all I'm doing is just taking each component and doubling them, no problem. Okay, if I want to get the vector between 2 points, all I'm going to do is the destination minus the origin. So notice the origin is P1, the destination is P2. How do I get the vector? x2 take away x1, y2 take away y1, z2 take away z1. Again, very, very simple to demonstrate this one. Let's make up a random destination. Let's say our destination is 4, 4, 4, and our origin is -2, -3, -7. Okay, so I'm trying to join that destination point to that origin point. What is the vector that connects those two together? To do this, I'm going to do destination minus origin. 4 minus negative 2, 4 minus negative 3, 4 minus negative 7. Okay, and I'm going to call this vector u. Okay. Now, of course, this vector by itself has nothing to do with either of those points. The vector does not. The vector is just the instructions for how to get from one point to the other. But if I were to do O plus U, if I start at O and then add this vector, I'm going to end up at D. And if I do vector OD, I get the same thing as vector U, right? 6, 7, 11. Okay, so remember, the vector is simply a set of instructions for how to get from one place to the other. A vector by itself is not a location. You don't know where it is. You just know in what way it's pointed and how long it is. Okay? But in any case, you can get a vector to join 2 points together. Very, very simple. Destination minus origin, you're done. 2 vectors are equivalent if the 3 components are equivalent. It's the only way the 2 vectors can be equivalent. Okay? Again, the unit vectors I, j, and k, we have a special name called basis vectors because they basically create 3 space. If you have a vector I, j, and k, you can express any other vector in 3 space as some combination of those 3. Okay? It says any vector can be uniquely represented in terms of those basis vectors. And again, this is a very simple idea. It would be just something like this. Vector v is equal to, 1, 4, 3. And therefore, you could also say it's equal to... I know this is a pain to watch, but I have to type this out properly, otherwise. I hat... Right, so it's I hat... There we go. Right, plus j hat plus k hat. There we go. Okay, now, this vector would be the exact same thing as I plus 4j plus 3k. And again, all that means is vector I is only going in the x direction. We need one of them because it's magnitude 1. Vector j is only going in the y direction. We need 4 of them because it's magnitude 4. And vector k is going in the z direction, and we need 3 of them. So it's very, very easy to change something into basis vector format. Basically, you just take the 3 numbers, stick an I, j, and k beside them, get rid of the commas and the brackets, and add plus signs. And if the points are negative, you can use a subtraction sign too, of course. Okay, let's try an example. So here it says vector u is 5, negative 6, 3. Vector v is negative 3, negative 4, 7. And then we have these 3 points. What we're supposed to do is find 8v, take away 2u, 2u, take away 3v, ba, and then this. Now, this first question, A, you might be looking at this, in the context of last assignment and going, oh man, I got to draw this complicated thing and so on. But really, this is not that difficult. All I'm going to do is write down 8, then write down vector v, then subtract 2, and then write down vector u. Now I'm going to do the scalar operations, negative 24, negative 32, and 56, minus 10, negative 12, yeah, right, and 6. Okay, and then I'm just going to subtract these 2 things. Negative 24 take away 10 is negative 34. Negative 32 take away negative 12 is negative 20. And 56 take away 6 is 50. Okay, now again, this is easily checked, right? So open up GeoGebra, go into your 3D view, you don't even need 3D view, go u equals 5, negative 6, 3. Okay, v is equal to negative 3, negative 4, 7. Okay, and then you go 8v minus 2u. And lo and behold, it comes up with negative 34, negative 20, 50. Right? Very, very straightforward operation. This is not a complicated thing to do with component vectors. It was a complicated thing to do with bearing vectors, but we don't have that problem here when we're working with components. Okay, next thing. It says find the magnitude of 2u take away 3v. Okay, so how do you do the magnitude of 2u take away 3v? So stick the magnitude sign on there, and then write your vectors out again. So v was -3, -4, 7. U was 5, -6, 3. Okay, do the operations and do the magnitude at the end. So there's my magnitude. Now my first vector is 10, -12, 6. Subtract -9. Actually, you know what I'm going to do here? I'm going to add, and I'm just going to distribute the negative into the bracket. So 9, 12, -21. Okay, so you see what I just took the -3 and went into the bracket. So I'm looking for the magnitude of 19, 0, and -15. Right? How do I get the magnitude of a vector like that? I remember that the magnitude of any vector is equal to the square root of each component squared and added together. Okay? And so I'm just going to find the square root of 19 squared plus 15 squared. Get 586. Take the square root of 586, whatever, 24.21. Let's just leave the answer. It's a better habit to be in to just leave the answer like this. So 586. Okay? Again, let's check our answer here. So I'm going to type, I already have the vectors programmed, so I'm just going to type 2u minus 3v, and then I'm going to type length c, and the length is 24.21. If I want to know the exact value, I'm going to square that number, and then I get 586, and I know it's square root of 586. Okay, next thing it wants to know is vector BA. Now again, this is very easy to do. You do destination minus origin. So let's write the destination. The destination is A, 3, -1, 4. The origin is B, -3, 1, 5. Okay? To subtract those two, you get 3 take away -3 is 6. -1 take away 1 is -2. 4 take away 5 is -1. And so there's my vector. So vector BA vector BA is 6, -2, -1. Again, easy way to check this. Go back over here. We'll just type them in. A equals, remember it's a capital if you want to point, right? Otherwise it would draw a vector. If you want to point, you just type a capital. 3, -1, 4, then -3, 1, 5. So B equals -3, 1, 5. I want a vector that joins those two things. Let's go vector AB, right? And I think I was actually supposed to find vector BA, so sorry. So I'll type it the other way. Vector BA is equal to 6, -2, -1. And that's exactly what we said. Right? And that vector BA is just up here. I'll just hide this one. It goes from B down to A and just joins those 2 points in space. Okay? Okay, 5 times vector BC plus 2 times vector V. Okay, so first of all, we need vector BC. Okay, again, to get this, we'll just do destination minus origin. The destination is point C, -7, -4, 0. The origin is point B, which is -3, 1, 5. And therefore, vector BC is just going to be, -7 take away -3 is -4. -4 take away 1 is -5. 0 take away 5 is also -5. So there's vector BC. Now we need 5 of those, plus 2 times vector V. Vector V, remember, was -3, -4, 7. And we just do the arithmetic. So -20, -25, -25, plus -6, -8, 14. So we get -26, -33, and 11, -11. Okay? And this would be our answer for 5 BC plus 2V. Again, let me just quickly check this. So I'm going to input point C, -7, -4, 0. Then I'm going to go vector, so let's say BC equals vector BC. Okay, and now we wanted 5 BCs plus 2 V's, I think it was. right? Negative 26, negative 33, negative 11. Exactly what we said. Okay, here we go. 8I minus 5U minus 3J minus K. All right, let's do it the long way. You see if you can figure out a faster way of doing this. I don't expect you to do it the long way, but let's do it the long way just once so you can see what it would look like. So here we have 8 times the vector 1, 0, 0, minus 5 times the vector u. Vector u was 5, negative 6, 3. Minus 3 times vector j. Remember, vector j is 0, 1, 0. And then minus vector k, which is 0, 0, 1. Okay, so let's take this, move it back over to the left side of the page. Okay, and then underneath it, we'll just expand it out. So we have 8, 0, 0 minus 25. Actually, let's just do plus and distribute. Negative 25, 30, and negative 15. Then we have minus 0, 3, 0, and then minus 0, 0, 1. What's the final answer? 8 plus negative 25 is negative 17. 0 plus 30 minus 3 minus 0 is 27. And then negative 15 minus 0 minus 1 is negative 16. And so there's my answer for that one. Okay, again, as a quick check to that one, let's go 8, negative 3, negative 1. So we'll call this vector q. And then we're going to do q minus 5u, negative 17, 27, negative 16. Okay, good. Now, it wants the perimeter of ABC. Excellent question. The perimeter of ABC. And I'm going to leave... Oh, it says the area over here. Okay, so we have an area question already. So perimeter of ABC. So let's do that. So let's just... I think we're done with this question after that, right? So let's delete everything except the points. So we can just kind of start fresh here. So first of all, why would there be a perimeter to create? Okay, notice that 3 points in 3D, as long as they're not all in a straight line, form a triangle, right? You could create a triangle here. You could do so if you just typed polygon ABC. And you could see it creates a triangle. It measured all the lengths for me, as well as the area of the triangle. Of course, I'm going to want to see how you do that, but for now, I mean, just being able to check your work, right? This is pretty helpful. How would I get the perimeter of this triangle? So the perimeter of ABC would be equal to the magnitude of AB, right? Because that would be like the side from A to B, plus the magnitude of C, or AC, sure, plus the magnitude of, let's say, BC. I mean, really, you could say CB. It makes no difference, but whatever, right? As long as you do all 3 sides, you can do this. So you can get the perimeter of this triangle. What we need to do is we need to find a vector AB, AC, and BC. Now, from our work above, we already have a vector BC. So let's write that down so we don't lose it. I think we also have a vector AB, don't we? So here's our vector AB. Now, it actually is BA, but of course, it doesn't matter because all I'm looking for is its magnitude, right? And its magnitude is just going to be the square root of those numbers. So whether it's pointed forward or backward, it has the same magnitude. The one we did not get here is AC. CA is also fine, but AC. Okay, we didn't get vector AC, so let's get vector AC. So let's just go back up to the points for a sec. So to get from A to C, how would I get there? I would go negative 10 in the X, I would go negative 3 in the Y, and I would go negative 4 in the Z. So negative 10, negative 3, negative 4. Again, a quick check here. Vector, so let's say AC equals vector AC. And I get negative 10, negative 3, 4. Let's check my other work just while we're here. It's easy enough to do. BC equals vector from B to C. And BA equals vector from B to A. Okay, and everything I have is right. Now, to get their magnitudes, right? So to get, let's say, magnitude of BC would be, right, you take the square root of -4 squared plus -5 squared plus -5 squared. Okay, so the magnitude of BC, I'm just going to drop the vectors for speed here, but you know you need to write them when you're showing me your work. 16 plus 25 plus 25, so that's root equals, so the magnitude of this one is square root of 66. Okay? Again, let's just do the other ones in our heads. So BA, the square root of, for vector BA, right? 6 squared is 36, 2 squared is 4, 1 squared is 1. So 36 plus 4 plus 1 is 41. And magnitude of AC, you would get 10 squared, which is 100, 3 squared, which is 9, 4 squared, which is 16, just square root of 125. And so the perimeter of this triangle is just equal to those 3 roots added together, the sum of the roots. So the approximate perimeter, let's say we wanted to give, let's say we were typing it into D2L for our answer. The approximate perimeter, we would just go square root 66 plus square root 41 plus square root 125, and we get the answer 25.71. Okay, again, you also have the option on GeoGebra. You can make an error there because it's not getting the same number that. Oh, sorry, this gave me the area, not the perimeter. That's why. Okay, just getting mixed up there. You can also do length, remember? Length AC would tell you the length of that vector. Length BC tell you the length of that vector, and length BA would be the length of the final vector. You can just add these together. E plus F plus G gives you the 25.71, which is the perimeter. Okay, so again, very common question, the perimeter. Not very difficult, but you do need to know your stuff in order to get it. Okay, here we go. It says if this point, or this vector plus this vector plus this vector equals this, find x, y, and z. Again, a question that looks difficult but is actually quite simple. Consider the x component first and just write the x component. Okay, let's follow just what's happening with the x component. We have 1 plus 2x, take away 2 times 3 equals 3. Okay, so again, how am I getting that? Here's the x component, here's the x component, here's the x component, so I'm only working with x. Okay, therefore I determine. Sorry, and this shouldn't say equals. This is just use an arrow here, so we're not. Okay, so what do I get here? 1 take away 6 plus 2x equals 3. Therefore, 2x is equal to 9. Take away 1 is 8. X equal to 4. Okay. Again, might be good to can check that. I guess we can put this after. So let's go A, B, C, and then I'm going to go 1, B, -1, plus 2, A, -2, 0, minus 2, 3, -3, C equals. Okay, yeah, well, so we need it to be 3, -2, 7. So what I said there is that the x component should be 4. If the x component's 4, okay, then our answer is right. Then we go on to the y component. So y component. Okay, y plus 2 times -2 minus 2 times -3 equals -2. Right? So just solve this. Y equals, let's send everything to the other side. So a -4 on the left becomes a +4 on this side, and a +6 on the left becomes a -6 on this side, and we end up with y equals -4. So if I make y -4, you can see my vector now has a -3. Now it's supposed to have a -2. So I'm thinking I made a mistake here. Let's just quickly check this over. This is -4. It comes over as +4. This is +6. It comes over as -6. Okay, maybe I made a mistake here. Oh yeah. There we go. Okay, now the final component, to get the z component, again, you just focus on z. So we get -1 plus 2 times 0, take away 2 times z equals 7. So we get 2z, let's bring 2z to the other side. So -1 take away 7 equals +2z. So -8 equals 2z, -4 equals z. And so c also has to be -4. And then we get the vector that we wanted, right? 3, -2, 7 is our answer for this equation. So we found x, we found y, we found z. All right. Given triangle ABC, show that the triangle is right-angled. Calculate its area, calculate the perimeter, and then determine the fourth vertex needed to complete a rectangle. It's a really good question. Really, really good visualization question. Okay. All right, so let's start with a picture, and we'll see what we can do. So again, my advice when you're looking at one of these questions, go ahead and graph it. So type A, -1, 3, 4. B equals 3, -1, 1. C equals 5, 1, 1. Okay, now take a look at it. Yeah, it looks like it could be a right angle, and B is probably the right angle. Again, let's say I'm struggling here. I'm having trouble visualizing it. Type polygon ABC. Now I can see the triangle. And if I look at it, sorry, I'm not looking at it. You can't see what I'm doing. If I look at it over here, you can see, yeah, it's a triangle. And it looks like it has a right angle. Now, how would I show that it has a right angle without looking at it? So show that the triangle is right angled. Okay, I don't really know what to do here. So what I'm going to try, let's just start with what we do know how to do, which is we know how to get each of the vectors. So vector AB, for example, how would I get from A to B? To get from -1 to 3, I'd have to go 4 in the x. To get from 3 to -1, I'd have to go -4 in the y. To get from 4 to 1, I need to go -3 in the z. So there's vector AB. AC, okay, vector AC, how do I get from A to C? I'd have to go 6 in the x, right, to get from -1 to 5. To get from 3 to 1, I'd have to go down 2. To get from 4 to 1, I'd have to go down 3. Okay, vector BC, okay, to get from B to C, I'd have to do from 3 to 5 is +2. From -1 to +1 is +2. From +1 to 1 is 0. Okay, so I have those three vectors. So the three sides of my triangle are, okay, what are the three sides of my triangle? So again, let's just do this mentally. Just an absolute mystery how this program works sometimes. Why are you over there? Okay, the three sides of my triangle. So AB, the side of, or the magnitude AB, would be 16 plus 16 plus 9, which is 32 plus 9 is 41. So square root 41. Okay, magnitude of AC would be equal to square root, let's see here, so 36 plus 4 is 40, plus 9 is 49. So that one actually is kind of nice. We know square root of 49 is just the number 7. And then we have square root BC, which is the magnitude here would be 2 squared plus 2 squared, which is square root 8. Now, is there a way I could use this information to prove that it's right-angled? To show that ABC is right-angled, show that a configuration of its sides follows the Pythagorean theorem. So, for instance, take the longest side squared, right? Would have to equal the sum of the squares of the shorter sides. Let's see if that works. My longest side here is clearly the square root of 49. So my longest side is 7 squared equals root 41 squared, which is 41, root 8 squared, which is 8. And so I get 49 equals 49. Therefore, ABC is a right triangle, and AC is the hypotenuse, and therefore the 90-degree angle is at vertex B. Okay? Now let's check that conclusion with the picture. If I click angle and then click my polygon, right? You can see the angle down here is 90. The angle over here is 66 and 23, but it does make a right angle triangle, and the right angle is located at B. But notice I don't actually need the picture to get any of that. I just need to think about the three sides and whether they have a relationship the kind that the Pythagorean theorem would say they should. Now calculate the area of ABC. We know that the area of is equal to the base times the height divided by 2. We also know that in a triangle, yikes. Okay, we also know that in a right triangle, the hypotenuse is neither the base nor the height. The other sides are the base and the height, so you can pick whichever one you want. So since we know that AC is the hypotenuse, let's say AB equals the base and CB equals the height. You could do it the other way around, it doesn't matter, as long as you don't make AC the height, because AC is, of course, the hypotenuse. So how do you do this? The area, right, would be equal to the base, which is, in my picture, is root 41. So I'm going to do square root 41, okay, times square root 8, okay, and all of this divided by 2. Now, to simplify this root a little bit, just to remind you how to do that, you can multiply the 41 times the 8 inside the bracket, so you get, actually, you know what, I want to do this a bit differently. 41, let's actually break up the 8. So instead of thinking about it as root 8, let's think about it as root 4 times root 2. Okay? And the reason I'm doing that is because I want to simplify this a little bit. And so you get the area is equal to, now root 41, don't think there's anything I can do with that. If you're ever not sure if you can do anything with that, you go prime factors 41, and it's a prime. It doesn't have any factors, so there's no way you can make that any simpler. So you're gonna do, all you're gonna do here is, what you can make simpler though, is we could say root 41. Now root 4 we know is just equal to times 2, and then times root 2, and then all of this needs to be divided by 2 at the end. So the 2's and the 2's cancel out. We get root 41 times root 2, which is a square root of 82, and that would be the area of the triangle. Let's compare that with GeoGebra's answer. It gives the answer 9.06 for the area, so I'm going to compare that number to the square root of 82, and you can see that, you know, down to the 5th decimal, they're the exact same number. So the area is there. Calculate the perimeter of ABC. Again, very, very simple. ABC equals the magnitude of AB plus the magnitude of AC plus the magnitude of CB. And ABC here, it's just equal to 7 plus square root 41 plus square root 8. Nothing you can do with that, so you just add it all together. if you want to change root 8, you could make root 8 a bit simpler. You could say ABC equals 7 plus square root 41 plus, and then the square root 8 you can make simpler by saying it's 2 root 2, because you can factor out a pair of 2's, but I don't really think you need to worry about that. Now the last question is really interesting. It says determine the fourth vertex needed to complete a rectangle. Now, looking at this picture, you can see where such a vertex would have to go. It would have to go up here in this corner. There's no other place it could go. However, right, that we should use this as an opportunity to discuss parallelograms in 3D. So suppose I wanted to say, let's say AB equals vector A to B, AC equals vector A to C, and BC equals vector B to C. Okay? Suppose I took the point, if I started at point B, actually sorry, let's start at point C, and see what would happen if we added these vectors together, right? So let's say a C plus a negative AC, so it's like and then plus a negative CB. I don't have vector CB, sorry, so put BC. Right? So okay, sorry. So there's your parallelogram. So if I stick D in that corner, so if I started at C and went across to A and then followed this vector over, I could create a parallelogram over here. Right? So you see how that's done? So you can create a parallelogram going out that way. You could create a parallelogram starting at B and working your way out that way. Or you could create a parallelogram starting at A and working your way out this way. Right? So you can see there's different ways of doing this. You can get a bunch of different parallelograms here. Let's draw one. So let's draw the one I just made. We'll use a different color. This is not what I was asked to do, by the way. I just wanted to show it to you. So we'll make it blue. Okay, so there's one way you could make a parallelogram. You could start at C, you could add vector CA, and then add vector CB. That would give you one possibility. So let's just write this down. So one possibility for a parallelogram would be to start at point C and add CA. So go C plus vector CA plus vector CB. And again, I am going to put these in vectors so that I'm clear. I'm not talking about points. I'm talking about vectors. So CB and vec CA. Okay. One possibility would be start at point D and find point D, which is equal to starting at C. So let's look at the picture again. Start at C, add vector CA, that gets you to A, and then add vector CB. That sends you out in this direction. And there, that point D will complete a parallelogram. Another point we could use to complete a parallelogram, let's see if we can apply the same thinking. Another parallelogram would be start at point A and find point, let's call it D2, whatever, is equal to A. We'll start at point A, then we're going to add vector AC, and then we're going to add vector AB. Okay, so what happens if I do this? So D2, call it D2, equals A plus AB plus AC. What did it just draw? It drew a point over here, right? That also would create a parallelogram. So now I'm going to go polygon D2 CAB. Okay, it also creates another possible parallelogram. We'll make this one green. Right? That's sort of poking out to in the other direction. Right? So it's like the D point was going over this way. If we start at the A point, we could create a parallelogram going over this way. Now the final way to do this, and of course the answer to the question, is what if we were to start at point B and generate a parallelogram? And point B would be special because point B has a 90-degree angle. Sorry, not point B. Yeah, sorry, it is point B. Just the beta was messing me up. Okay, it has a 90-degree angle, so its parallelogram would also have a 90-degree angle, and that would make it an actual rectangle, not a parallelogram. according to the thing we've come up with, right? What would be the means of getting there, right? So start at point B and find point D3, which would be B plus vector BA plus vector BC. Okay? And what would that do? I would start at point B, add vector BA gets me up here, add vector BC gets me right here, which is exactly where I need to be. So let's do that. B plus, so let's call it D2 or D3. B plus vector BC plus, and then I'm going to do a negative vector AB because I don't actually have a vector BA, right? All I have is an AB right here. But I know that BA is just the negative of that one. So that's why I'm writing negative AB. So that point up there in the top corner makes a rectangle. So watch when I draw a polygon, B, C, D3, and A. And this is, of course, the answer that we actually want in the question. This one, we'll make it pink. Okay, that rectangle is the answer. Where would the point be? Where would I find this point so that I create a rectangle? The idea, if you draw this in 2D, you will find it. So let's just do it quickly on paper. So I want to start at point B and add vector BA. Of course, what would happen if I did that is I would be at point A. That's where I would be. So point A plus BC will be the final vertex of my rectangle. And so point A, let's go back up. Point A was located at negative 1, 3, 4. Okay, the vector BC, let's go back up and find vector BC. BC was 2, 2, 0. And therefore, the point I need, the point D, would be 1, 5, 4. Let's go back to my picture. Where is point D3? Exactly at 1, 5, 4. And if I draw it, I see that it makes this rectangle. So again, you don't need to do all of this stuff with the other quadrilaterals, okay? I just wanted to show you that there's not, in case you were wondering why you need to start at point B in this question, if you started at point C or point A, you would create a parallelogram, but it wouldn't be a rectangle, right? It would just be a it would just be a parallelogram going off in a different direction. To create a rectangle, you specifically need to start from that spot so that when you draw it out, you create a 90-degree parallelogram, which another word for that is a rectangle. Okay, so that's it for today. Again, a lot of stuff to think about. Just try the homework and please post or reach out if you're having any trouble.